Asia Pacific Analysis and PD seminar. Let me introduce today's speaker. Today's speaker is Professor Masashi Misawa from Kumamoto University. He received his PhD around 1995, and he, under the guidance of Professor Kikuchi, and he's a specialist of the variational problem, especially specialized on P Laplacian, the P Laplace dirichlet energy. And today, he's going to talk. He's anyhow top specialist on this field, and he has a lot of joint work with other specialists in Europe. Today, he's going to talk on concentration phenomena for the Sobolev flow. Please.
Thank you. Firstly, thank you for your kind invitation, Professor Giga Sensei. I would like to thank the organizers, in particular, Professor Giga Sensei and Professor Howard Sensei, for giving me a nice chance to this Asia Pacific Analysis and PD seminar. Today, I would like to talk about the gradient flow equation for some variation problem associated with the Sobolev inequality. The title is the concentration phenomena for the P-Sobolev flow. Firstly, I would like to explain the equation we consider in this talk. This is our problem, and the first line we have the equation. It's a little bit. This is the complicated for at first glance, but I try to explain this equation. The time derivative of q minus 1th power of the absolute value times u. U is the unknown function, and minus the special divergence of p minus 2 power Euclidean norm of spatial gradient of u times spatial gradient of u is equal to real valued function lambda of time t times q minus 1 power absolute value u times u. This is our equation. You know that we have two kinds of power nonlinearity in time derivative, and in the second order special derivative. You know, this second term is called P Laplace operator. And the first term is a porous medium type operator. So left-hand side is just constructed by combining the porous medium operator and the P Laplace operator. So in this sense, we call this left-hand side is a double nonlinear parabolic type operator. So the equation in the first line is called the double nonlinear parabolic type equation. Okay, so we consider this first equation with some constraint, and that is q plus 1's integral on space of u is equal to 1 for all time t. And this is just a constraint for this first equation. We consider Cauchy and not the boundary problem for this double nonlinear parabolic type equation with this constraint is the second line. This is our equation. I want to call this equation is P Sobolev flow. In particular, P Sobolev flow. Simply saying Sobolev flow. Okay, and domain omega is a bounded domain, n-dimensional Euclidean space. In this space dimension, which is larger than equal to 2, the boundary omega is smooth. Then we have two kinds of exponent, p and q. The p is larger than 1 and less than the n. Q satisfies the following relation. Q plus 1 larger than equal to p and less than equal to p star. P star is so-called Sobolev critical exponent, which is defined space dimension n times P over space dimension n minus P. And initial condition U0, initial data U0 satisfies the following condition. Initial data is U0 belongs to usual Sobolev space in omega, W1P omega, with zero boundary value in the torus sense. And U0 is positive and bounded, positive and bounded. Also, Q plus 1's integral in space U0 is equal to 1. These are assumptions of the initial data. Before going to the main theorem, in this talk, I would like to explain some properties of the P-Sobolev flow. The first one is about the real valued function lambda in the right-hand side in our equation. Lambda is actually computed as piece-powered integral of spatial gradient of U for each time section t. Indeed, multiply our equation in the first line in the solution U and integrate on space omega formally. Then we have the following integral formula in equality Q over Q plus 1 Q plus 1 times time derivative of Q plus 1's integral in space ut plus piece-powered integral spatial gradient of U is equal to lambda t times Q plus 1's integral of ut. Here we use the constraint in the second line. That is Q plus 1's integral is equal to 1 for all time t. Then this term equal to 0, and this term is 1. Just we get lambda t is equal to piece-powered integral gradient of U. So we can regard this function lambda t is a Lagrange multiplier for our equation under this second this volume constraint in the second line. And now I look at the equation more precisely in the first line. The left-hand side, the double nonlinear parabolic type operator. If Q plus 1 larger than P, then this operator is so-called first division type operator. So considering this equation, then solution should vanish at a finite time. So this is a typical property of the left-hand side operator. And next we look at the ODE part. So formally removing the second term in the left-hand side, then we get this ODE equation. Please, we can see the power nonlinearity is the same in the both sides. So of course, this solution is given by such exponential type function. So solution U is a positive and bounded for all times. So I think that these two kinds of effect makes the solution is positive and bounded for all times. So we can expect the global existence solution is a very rough consideration, but this is just my expectation for this problem. So now I would like to state the geometrical background for this equation. In the case P equal 2, So second operator, P Laplace operator becomes usual Laplace operator in the case Pico2. And we suppose a domain omega is a compact smooth Riemannian manifold. Then our equation, the system of equation is becomes Yamabe flow, so-called Yamabe flow for Yamabe problem, as a gradient for Yamabe problem. And as the equation is the first line and the constraint is the second line, equivalently converts to the following scalar curvature equation. Heat operator acted on a scalar curvature R is equal to nonlinear quantity, quadratic nonlinearity on scalar curvature. This is a very key point to observing the existence of solution and asymmetric behavior Yamabe flow. The firstly, such geometric structure is observed by Richard Hamilton. Later, for instance, Michael Strube, Professor Strube, and Schuberick and Simon Brando, by use of this such beautiful geometric structure of this the Yamabe flow, they consider and get the nice, excellent results for Yamabe flow. And so wait, sorry. And next, we look at the variational structure our equation, the system of equation. Let EU be as the P energy, which is defined as P, the 1 over P times P's powered integral of spatial gradient of U. We consider this P energy in the space, the Sobolev space, satisfying this constraint that is Q plus 1's integral is equal to 1. And now we try to compute the first variation of this variation problem. And so we put the comparison map U plus real parameter tau times phi over Q plus 1's integral of Q plus tau times phi. Here phi is a smooth function in omega with compact support. You know, this is just the admissible comparison map for this variation problem. So we can write this quantity, the gradient flow, gradient vector field, P energy, with direction phi in the distributional sense. Also, directly computation gives us the representation, this first variation. This is a very simple computation. Finally, integration by parts. This first variation is equal to minus P Laplace operator U minus P energy times Q minus 1's powered absolute value U times U, totally producted phi integrated on omega. This is the presentation is the first variation. So we can regard the gradient vector field P energy is equal to minus P Laplace U minus P energy times Q minus 1's powered absolute value U times U. So our equation first line is regarded as such OD equation in the Sobolev space with satisfying the volume constraint. So, but here is not regular form. Time derivative is not regular form. So not exactly the gradient flow, but gradient flow like equation. The first equation is regarded as gradient flow-like equation. So this is a variational structure for our equation. And the lastly, I want to look at the Euler-Lagrange equation. Then now we consider a non-negative and bounded weak solution, this elliptic type equation. This is Euler-Lagrange equation, and with boundary value 0. It is well known that if q plus 1 is equal to Sobolev critical exponent, this which is called the Sobolev critical case, and domain omega star-shaped, then solution should be trivial. This is verified by Positive identity and Hopf maximum principle for P Laplace operator. But I want to make one comment here for P Laplace operator. P Laplace operator is a degenerate and singular elliptic operator, so to show the validity, Positive identity, and Hopf maximum principle, we have to the regularization, the usual regularization of P Laplace operator. Anyway, we can show the positive identity Hopf maximum principle holds true for P Laplace operator. Then we have this result. Also, we look at recall the usual Sobolev inequality denoted by SI. Sobolev inequality is the following inequality. C naught times Q plus 1 integral bounded by piece integral norm of spatial gradient V. This inequality follows Sobolev space W1 omega with trace boundary 0. In the case Q plus 1 equal to Sobolev critical exponent. C0, the constant C0 is characterized as infimum on comparison map, piece integral gradient of V. This is well known. And also, we know that omega, if omega is bounded, then this constant C0 is never be attained. On the other hand, if we consider Sobolev inequality from the whole space Rn, the corresponding Euler-Lagrange equation is minus P Laplacian V equal Q powered in Rn. We consider positive solution. This solution is precisely given by this formula. This function is called Tarenti function. Here we let that A is a real value constant, and XL is a Rn vector. It is well known that Tarenti function is attains the Sobolev constant C0 in Rn. What is the relation to our equation? If let Vx denoted by VAXLX, AX0 is free from choice, and then our stationary equation corresponding to our evolution equation, that is minus P Laplacian W equal lambda times Q powered W. The solution W is given by this formula by use of Tarenti function, just the transformed by scaling transformation. Okay. So what is the problem in this talk? The problem is that of course the global existence, weak solution, and regularity weak solution, our problem is here. Time derivative q squared u minus p Laplace operator of u equal to lambda t times q's power u. With constraint q plus 1's integral is equal to 1 for all time, our equation. Of course, finally, I would like to study the asymmetric behavior of this solution, global solution. What is the limitation is at infinite time of solution ut. Previously, already we explained the corresponding stationary equation is like this. So cube in the case that q plus 1 is equal to critical exponent and omega star shaped, then corresponding stationary solution should be trivial. But our equation should satisfy this constraint q plus 1's integral is equal to 1. So rough, very rough, it is very rough observation, but the limitation in this situation, q plus 1, that q plus 1 is equal to p star and omega is star shaped. The corresponding station should be 0, but our solution should satisfy this volume constraint. We call this quantities volume constraint. So limitation satisfies compensate such a volume preservation. So we can expect that some volume concentration at some parts in domain. And this is called volume and energy concentration. We can expect such volume energy concentration at infinite time for our solution. This is our motivation and question. Firstly, we show the first result is about global existence of weak solution and regularity of weak solution. We have a global weak solution denoted by U belonging to this function space, the continuous on time in of Q plus Rubik space LQ plus 1 omega, and L on time is Sobolev L on time of Sobolev space W1P0 omega. U is global weak solution, and Lagrange multiplier like constant real value function lambda t is P energy of a solution U for each time section t. And also U is positive and bounded for all finite time interval. And finally, this solution U and its spatial gradient is locally in time space held continuous. Locally in time space held continuous. And this is which is a regularity of weak solution. Later we have time, then I would like to explain the precise proof, but I want to emphasize that such positivity solution is very important in our proof. You know that our equation satisfies the so-called comparison principle, but in the case that the Q plus 1 is equal to P star, which is a Sobolev critical case, we have no good comparison function to show the positivity for all time. And so I have to care for positivity, the positivity of solution U. This is based on so-called the expansion of positivity, which is, in other words, weak Harnack inequality. But later, if I have time, then I would like to show the detail. And also our weak solution, weak solution that satisfies the following energy inequality. Time derivative L2 norm in time space of time derivative of q plus 1 over 2 powered of u is bounded by initial p energy. And the essential supremum T of P energy is also bounded by P energy. This is just energy inequality for our weak solution. If Q is larger than equal to 1, then the first energy inequality gives us the L1 norm in time space of time derivative Q's powered U is bounded. This is a little bit important to investigate the asymptotic behavior of our solution. This is global existence of solution regularity and energy inequality. The second theorem is about the asymptotic behavior of a solution of P Sobolev flow. Now we suppose P is larger than or equal to 2 times space dimension n over space dimension n plus 2 and less than space dimension n. And we suppose Sobolev critical case that Q plus 1 is equal to P star. We take a time sequence denoted by Tk diverging to infinity, and also the sequence Raddi denoted by Rk decreasing to 0. Then we have a sequence of another time sequence of tau k, which diverging to infinity, which depends on Tk. And also we have the finite integer capital N, and we have n number of points denoted by xi in omega. And we have a subsequence Raddi denoted by Rki of Rk. And also we have a sequence real valued denoted by Lki diverging to infinity for each I from 1 to capital N, such that the following formula holds. Ux is now, I want to show the asymptotic behavior of solution U along the time sequence tau k. So this is the solution along the time sequence Ux tau k converged to infinite time. Okay, so as tending to k infinity, Ux tau k converged to second term and the third term. Second term is just the concentration part, and the second term is some so-called body map. So just Ux tau k is basically converged to infinity with remainder the second term. Second remainder term is given by concentration quantity. Okay, so infinity is a non-negative bounded weak solution of the corresponding the stationary equation in omega. The lambda infinity bar is a positive constant here. And the infinity and the gradient of infinity is a uniform Helder continuous domain omega. And about the second term, this is important for our talk. WI, we denote this is WI, is a positive and bounded weak solid of corresponding stationary equation in whole space Rn. Here, lambda infinity is a positive constant for each I from 1 to capital L. The Wi and special gradient Wi is also locally held continuous in the whole space. And we have the following volume and energy decomposition along the solution and time sequence tau k. Sorry, this is a mistake. This is tau k. Not tk. This is tau k. Sorry, this is misprint. Anyway, q plus 1's integral on space u tau k decomposed into q plus 1's integral u infinity. Q plus 1 integral of body map infinity plus concentration function. Sorry, Q plus 1's integral concentration function Wi here. The precise saying summation of Q plus 1's integral concentration function Wi. We have also the energy decomposition in this way. And okay, this is a main theorem in our talk. I want to emphasize the concentration compactness in finite time, our P-Sobolev flow. For the proof of, from now, I want to explain the outline of the theorem. For this purpose, we need some theorem lemmata. Now I show you the so-called epsilon strong compactness. We suppose P is the same condition that is larger than equal to same condition as theorem 2. Theorem 2, the same condition. That is P is larger than equal to 2 times n over n plus 2 and less than n. Q plus 1 is equal to P star. That is a Sobolev critical case. Tk is just the time sequence of time diverged to infinity. Then we have a subsequence. We have a sequence, another time tau k diverging to infinity, which depends on Tk. We also have a positive number, epsilon naught, and we have endpoints, finite endpoints xi in omega, such that the following formula and convergence hold true. For any small number r, and for any I from 1 to n, we have this formula. Limit inf as k tending to infinity of the time space integral. Here, this symbol means integral mean on time of q plus 1's integral in Vxi r ball with the center xi and radius r. Integrate on time interval tau k minus piece power r tau k and integral mean average here. This limit inf this time space integral quantity is larger than epsilon naught. So we can regard xi is a concentration point of volume in this sense. And also this is u tau k. Tk is a misprint. U tau k converge to U infinity, infinity body map as in theorem 2. This convergence follows through strongly in Sobolev space, locally in Sobolev, strongly and locally in Sobolev space, omega except n finite points x1, xn. So except x1, xn, we have a strong convergence as energy. And the next I want to state the volume and the energy concentration at the finite to n points xi. So the tk is the same as before. Tk is a sequence, time sequence divergent to infinity. The rk is a sequence Raddi decreasing to 0. Then we have a positive number epsilon 0. This is the same as theorem 3. And we have the sequence, another sequence of time denoted by tau k, divergent to infinity, which depends on tk. We have n finite points in omega denoted by xi. And also, we have a sequence, real numbers, denoted by capital LKI for each I from 1 to n. LKI is a divergent to infinity, such that the following formula and convergence fall true. The first one is almost same as the first formula in the theorem 3. Which means n finite points xi is a concentration point of volume in this sense. This quantity and this quantity in the theorem 3 is almost same. And secondly, for each xi, n finite points xi, we have the following convergence, scaling and blowing up convergence. So now we consider blowing up function denoted by vkx, defined as u x. This is defined as blowing up around the point x0. x0 is each n finite points xi. And here, scaling parameter is lk. The scaling order p minus q plus 1 over p. And this is tau k. The time variable is tau k. And this is blowing up function, which converges to wix. Wix is a concentration function, the same as in the theorem 2. And this convergence is strongly and locally Sobolev space and Rubik space LQ plus 1 in Rn. And this is just the strong convergence blowing up function. This is main part. Okay, I have more 5 minutes, so I try to explain the outline of theorem 4 and theorem 3. Okay, so the theorems, the proof of theorem 3 and theorem 4 is based on so-called local boundedness of our solution is a piece of the flow. So now I would like to show you local boundedness results, our equation. Suppose that P is larger than 1 and less than n. Sobolev critical case, Q plus 1, that Q plus 1 is equal to P star. And now we suppose U is a non-negative weak solution This is our double nonlinear parameter equation. A0, A naught is a positive number, R not positive number satisfying this one. So this equality means R not is very small, is a P energy of initial data. Q is a local region. This is figured as in this way, time space region. This is just Q, and also is a more smaller than a smaller region, Q prime, denoted by Q prime here. So if this integral quantity, local in time space Q plus 1's integral is bounded by A naught. Sorry, this is also integral mean on time space. I mistake writing the integral mean. Here I put integral mean on time space, time integral dt. Integral mean, sorry. This quantity is bounded by A naught. Then we have local boundedness in this way. Local is a essential supremum Q prime. Q prime, as stated before, smaller than firstly fixed local region Q, in figured as this way. Essential supremum of U is bounded by this quantity. Please look at the boundedness. Here is this quantity depends on the R naught and the delta naught. Delta naught just depends only on N and P. So this is a uniform constant. Okay. So this time space integral quantity N bounded by N naught, then we have such uniform boundedness, smaller region Q prime. This is local boundedness results. Sorry, I have no time, but based on the local boundedness, then we can show the validity theorem 3. Okay, so for the proof theory 3, we choose X naught in lemma 5. Any point X outside n finite points, finite endpoints. N finite points Xi is regarded as a concentration point. Now we take X arbitrarily outside of a concentration point. So we choose X0 is this not the concentration point X. The R0 is a small number R, and then outside is the concentration point, then concentration point. This quantity, also mistake. This is I take integral mean. I have to take integral mean on time. Is smaller than equal to 2 times epsilon naught. Then lemma 5 yields such local boundedness. So this is combined with the usual weak convergence. Then we have the limitation of U tau k, denoted by U infinity, is non-negative and bounded weak solution. This one. At 1 minute, please. Next. Okay, so next, I want to show the very briefly the outline theorem 4. The strategy is the same as the theorem 3, based on local boundedness, lemma 5. So by use of volume constraint, then this quantity is naturally is bounded to 1. So we choose A naught in lemma 5 is just 1. So then lemma 5 means such a local boundedness in a smaller region Q prime. So the right hand side depends on RK. RK is a sequence Raddi increase decreasing to 0. So depends on RK. We denote this quantity by capital LK. So with the scale parameter as LK, we make a blowing up sequence functions denoted by VK in this way. Then through the elementary observation, orthodox usual observation, in particular, I want to emphasize Q plus volume, Q plus 1 integral P energy and L2 integral of this time derivative is invariant and under this scaling transformation. This is hold true only in the case that Q plus 1 equal to P star. That is a Sobolev critical case. So, okay, so now thank you for your kind attention. I would like to stop my talk. Thank you.
Thank you very much for your very nice talk. And are there any questions and comments? Please unmute yourself. Okay, I have a one question.
Yeah.
Let me start my question.
Yeah.
You are page 7, page 6. In your key lemma, you have
Yes.
no. Page 7, sorry, 7. Main theorem, sorry. I
Yes.
don't understand main theorem, theorem 2, I think. Yeah, this is one of main theorem. Good.
Yeah.
Could you tell me the role of TK? TK is just sequence, but in the later statement, I don't find TK. If you replace TK in the tau K, what's the role of TK?
Okay, thank you. Kind question. But firstly, we take arbitrarily the sequence of TK, but but I need to choose a sequence of another tau K because this is depend on the guaranteeing the convergence of integral of time L1 integral of time derivative to 0. So some integral mean by integral mean theorem, we can choose tau k in the interval determined by tk. So tau k is not the subsequence tk. So when very rough speaking, tau k is chosen as interval tk minus 1 tk.
I see.
Yeah, so very technical, sorry, but yeah, precise saying this is true. Yeah, because now I consider the evolution equation. So basically, integral quantity should be considered as a time-space integral, but the two studies limitation in the infinite time. We should consider the equation restricted on time section. So so then integral mean theorem on time variable, then we can choose. Then we choose the sequence new tau k in some interval determined by tk. So this is yes, but almost the subsequence tk. So no problem.
I see. So so you're saying no matter how so the way to choose TK is arbitrary. Just takes increasing sequence. Okay.
Yes.
Just okay.
Yes.
Good. Another small question. This is of course a Sobolev critical case. If it's not a Sobolev critical case, of course there's no concentration, right?
Yes, for instance, in the subcritical case, Q plus 1 less than P star, then yes, we can expect just convergence to body map denoted by infinity without concentration, I think. But
I see.
yeah, but I'm not sure because I don't make the proof in the subcritical case for our equation, but maybe it's
I
true.
see. Are there any questions? If you have a question, then please raise your hand. Daniel, please.
Yeah, so Professor Giga Sensei already asked my first question, what happens in the subcritical case, but I still have a second question, and that is if P is equal to the dimension, you would need actually, I think, to change your exponent to something else, or not?
Yeah. Your question is very nice for me. Maybe this is next challenge for me. Yes, yes, yeah. In the case of P called space dimensions, as you know, the nonlinearity, exponential nonlinearity.
Yes, exactly.
Yeah, of course, the Sobolev equality changed to reading a Mozart's inequality. I'm not expert now. I'm studying. So power nonlinearity changed to exponential nonlinearity.
But
So
would you expect the same phenomena as you described there? Because if you then replace the power by exponential,
I'm not.
The critical case, of course.
Yeah. Yes. In the case P equal to, that is the second P Laplace with a Laplace case is, for instance, Struve sensei, Michael Struve sensei studies the same equation in the P equal to and two-dimension case. But our equation in the P Laplace case, this is a very my interest, but very my interest. But P Laplace case, I'm not sure because P Laplace over log function U. Yeah, so I study the change to this is exponential is by V, the delta T V minus divergence P Laplace over log U, log V equal to lambda T V. So we have to study the log P Laplace operator. I'm not sure the fundamental result for this equation, but this is very interesting for me. Thank you. Thank you. Kind attention.
Thank you for the question. Are there any questions? Any comments? So let me ask another question, this fundamental equation. The stationary problem is fine, but if we talk about the non-stationary problem, why you choose the time derivative part like u mod u q minus 1 times q?
Yeah, this is, yes, thank you. Also, it's a very nice question to me because the only thing I like this double nonlinear equation. This is a half joking, but okay, sorry. But I want to put the same power nonlinearity time derivative in the lower order term.
I
Yes,
see, I see.
yes, then OD part is very, very good. The exponential equation, OD part is become. This is very important. Maybe this is very different from Giga Sensei equation. So this is my merit for our equation.
Thank you very much. Are there any other questions? If not, we would like to close this session, and there's coffee time.